Okay, in this little video I'm going to talk about the status and progress of my registration project. By registration we're talking about the relationship between the CT frame and the coordinate frame of a tracked ultrasound series, calling that the reference coordinate frame. And up until recently, I've been using normalized correlation, cross correlation, to compare the 2D images of the ultrasound slice and the corresponding CT slice. But now I'm experimenting with a different method that I'll show you. So here in the views, on the upper left we have the ultrasound slice. I can index forward and backwards through that. Here in the middle we have, in yellow is the CT slice that corresponds with the transducer, the track transducer position combined with the current transform of CT to reference. And then overlaid on that in blue, so that's yellow is the CT information. On blue is the same information that you see on the left from the ultrasound. That shows the overlay of the ultrasound with the CT for that particular slice. Of course, we have the 3D view here. Mainly this shows, so the box is the outline of the CT, and this little brassy shape here is the transducer. So you can, the purpose of this is to kind of show where the transducer is relative to the anatomy and to the CT. The anatomy is from the CT. The bones are from the CT. And down below we have just a log trace so that we can see what is going on. I'm going to talk a little bit about the algorithm itself. So in the algorithm, I wanted to get away from, I was having bad results with the cross correlation because there's so many features in one that do not show up in the other, mostly in the ultrasound. So there's a lot of features in the ultrasound. This ultrasound actually is dilated a bit. This is not the original ultrasound. This has been image processed. But anyway, there's soft tissue and other things that show up there. So the algorithm has to be independent of that. If we want to register to bone, then that needs to be baked into the algorithm. So what I've done here for this new algorithm is I have extracted just the bone edges that the transducer would see. So this is the first bony edge that the transducer sees from top to bottom. And again, that's also dilated, just to make, the purpose of dilation is so that the search is more is a little bit less sensitive, so that when you're close, you will start to be getting a signal, because the search doesn't do you any good if you only find something when you're right on top of it. And then over on the left, you can see the bluish color is the ultrasound, and then the yellow line is copied over from the CT. So the yellow line on the left is the same as the blue line on the right. And the scoring algorithm tries to get a measure of the alignment between these two lines. So basically the scoring algorithm right now is a ratio of the overlap is shown in white here where the colors mix. So the algorithm, the scoring function is the ratio of the white area over the yellow and white area combined. So basically, as a reference, the denominator is based on the bone edges from the CT. Because we know where the bone is in the CT, we don't know which of these features of the ultrasound at first glance. We don't know which features are bone. Especially, let me go to a different, we have a situation like this, right? So in this case, the ultrasound is reporting this. So this is a phantom. So this is molded into the phantom. The ultrasound is reporting this shape here, whereas the bone is actually way down here, and that shape doesn't really show up on the CT very well. And if I switch over, you can kind of see the bone edges a little bit in the ultrasound, but not very strongly. So actually, to get around that problem, I've cheated a bit, and I've cherry picked the slices. So I've only chosen slices for registration where for instance, like this one, where I expect the shapes to be pretty similar. Okay, so what I'm going to do now is I'm going to this initial right now. Before I started the video, I did a registration. So this is the result of the last registration. But just to show what it does, I'm going to kick the position off a little bit. So I'm going to move in 3 millimeters in that direction, 3 millimeters that way, 3 millimeters in the superior direction. And then I'm also going to add some rotations. I'm going to add 2 degrees, 2 degrees, 1 degree. And so now I think we can agree that the registration is off. So if you look at the blue shape versus the yellow shape, we're off by a few millimeters. And so let's launch. So now it's performing. It's using the Nelder-Mead or downhill simplex strategy combined with the scoring function that I described. So the scoring function, it takes the 6 degrees of freedom, the 6 values, X, Y, Z, in the 3 rotations, and it will shift the CT to that position, take the slice, the corresponding slice, and do the scoring method that I described. Now, of course, when you're doing the rotations, you still have to specify what point you're rotating about. In this case, I'm rotating about the center of the CT. I still want to improve that so that I can pick a better center. So it's done. It has it's changed. The registration algorithm did a shift of 5 millimeters, minus 6 millimeters, minus 6 millimeters. It did rotation of 1 degree in X, a little over half a degree in Y, and a degree and a half in Z. So let's just go through it and see if we think that that's a little bit off. There it starts to get a little more off. So it's better than the position that I put it to, but not quite perfect. Anyway, that's what I got for now. Thanks again for watching.